Alright, so I'm going to attempt to communicate some things about bases and I suppose coordinates. That was basically the first question. Was I'm a little bit lost about what a basis is. Can you help me visualize it? Something like that. Now I can't quite make good on that, but I can give you at least some simple examples of what's a basis. So maybe the simplest thing I should do is just go, okay, well, how about just R2? You know, if I have x and if I have y, then if I want a basis for R2, it's just going to be anything, pretty much anything. If I have two vectors, you know, like say this one, say that's vector A, and if I have vector B, you know, like this, whatever, they don't have to be perpendicular. Then if you pick any other point, in R2, you know, like this one, then you can use a linear combination of A and B to get down here, right? Like, it looks to me like maybe we do, now here's, I probably chose poorly. I need 1, 2, I don't know, about 2 and 2.6. I've got myself well, that's actually a minus B, this is a minus B, right? Minus 0.6B, roughly speaking. And then, I don't know, just eyeballing it here, but I guess that's about, what, 0.1A? So this point that I have down here, you might call it, I don't know, whatever you want to call this thing, Pac-Man. So as you can see, Pac-Man is something like minus 2.6 B plus 0.1A, or let's see here, more to my purposes, 0.1A minus 2.6B. So if I let my basis for the plane be the set A comma B, then the coordinates of Pac-Man with respect to the beta basis would be 0.1 and minus 2.6. Now, if you start thinking about it, as long as I have two vectors which are not collinear, I'm going to be able to reach any other point in the plane by taking linear combinations, and so that's what makes it a basis. And the coordinates of the basis are, well, of course, the most simple example would just be, you know, I mean, even easier. If you take my physics with me, I might call this y hat, I might call this x hat, and of course those form a basis, right? That's the standard basis. Or we usually use this notation here, E1, E2, right? Which is, let's see here, 1, 0, 0, 1, right? So that's the basis, forms the basis for R2. And so that's a starting point. Now, of course, in R3, right? In R3, we can still, at least I can still visualize. So if I take some point, you know, let's take some point in R3, I mean some vector really, right? Some vector, say this one. And if that vector is v1, v2, v3, okay, well then I can build that from tip-to-tail vector addition of, you know, like this guy, which might be v1e, e1, and then, oh man, lost my colors. Where's my colors? I'll use gray. I don't know, this one, which would be v2, e2, and then of course, up to the limits of my artistry here, you've got this vertical, well, this z direction one, v3, e3. So, you know, as a geometric rule, to give a base, so of course the basis here for R3, the standard Cartesian coordinate basis would be E1, E2, E3, and of course the coordinates of V with respect to this choice of basis, well, they're exactly the standard Cartesian coordinates. But this setup of a basis allows us to use non-standard directions, and they don't have to be orthogonal, and you know, you have a lot of different possibilities. You could, you know, let's see here, at the risk of making this too cluttered, you could do something like, I don't know, you could have your basic vectors be something like your base vectors. Like I could take this to be A, right? I could take this one to be B, perhaps, and then my C could be something like weird, I don't know. The only rule for R3, if I'm going to make A, B, C a basis, is that C can't be coplanar with A and B, right? It's got to be something that adds a third dimension, let's say. And so like this, for example, would do it. And then it's geometrically, I think, obvious that if you take any other point in R3, right, take any other point in R3, then you'll be able to reach it by taking a suitable linear combination of A, B, and C. So this what I might call, say, beta tilde A, B, C. It's a set of three vectors. They have to be linearly independent, and they have to span the space, right? I guess geometrically here it would correspond to them, if you look at them being the edges of a parallelepiped. That parallelepiped would have to be like non-degenerate. It would actually have to fill out some volume. And if you were to look at a specific point in space, right, and if you were to compare the Cartesian coordinates to the coordinates with respect to this beta tilde basis, well, they wouldn't agree, right? Because it would take a different number of A's, B's, and C's to reach a specific point than it would E1s, E2s, and E3s, because, you know, it's different. So, and so that's the idea of a coordinate system with respect to not necessarily perpendicular directions. You can go any, you know, you can have two coordinate directions 60 degrees separated, and the other one at 130 degrees to the other one, right? I mean, you got all kinds of possibilities, slant coordinate systems, and all sorts of things. All of these things are built into this concept of a basis, just in R3. Now that's the extent to which I can visualize. Past this, I have to do algebra, and that's what this course is about, is algebratization of problems. Visualization really, for most folks anyway, doesn't only get us to 3 dimensions. Past that, it's kind of hard. So let's see, a simple example that I can't personally visualize would be something like this. W, let's say, goodness gracious, how about A in R 3 by 3, such that A11 plus A22 plus A33 equals to 0. All right. Now, here's my intuition for this problem immediately. I start out with a raw template of R 3 by 3, right? And so that's a 9-dimensional thing. Then I've got this one real equation. Well, that's one equation. So I've got one equation, I got 9 independent parameters. I expect that this will be an 8-dimensional subspace just from looking at it. And so here's how you work it out. I mean, it's not, basically I say, okay, so I've got A, you know, is A11, A12. So what I do is I try to get my paws on what exactly a generic element in the space looks like, and then try to enforce whatever condition it is. That's a 3-1. You know, whatever condition it is that makes the subspace special, whatever makes it what it is. Try to impose that on a generic object, and then usually from that I can just rip off what exactly the basis should be. This one, for example, you know, you just got to pick. I'm going to either eliminate A11, A12, or so whatever you solve for, you eliminate. Tell you what, let's eliminate A33. So this condition gives me A33 is equal to minus A11 minus A22, right? And so you plug that down in here to your generic matrix. Everything's the same. Let's see here, A22, A21, I'm an idiot. That's a 1, obviously. A22, A23, A31, A32, and then A33. Well, A33 is minus A11 minus A22, right? That's a 2-2. I can't spell. All right. So then you just go, okay, well I can rewrite that as like that's A11 times what? Times 1, all zeros, except where? Minus 1. And then I've got, let's say here, plus A22, and then what happens? I'm just doing the interesting ones to start with 0, 0, 0, 0, 1, 0, 0, 0, and then a minus 1, right? And then what do I have? Well, then I've got, I'm going to use the other notation. Then I've got like A12, E12, plus A13, E13, plus A21, E21, plus A23, E23, plus A31, E31 plus A32 E32. I don't think he's hiding here, Isaac. And, uh-oh, I guess he is hiding here. He was founded. All right, so you look at it, and so there's these independent parameters, A11, A22, A12, so forth and so on, right? These don't have any relation amongst each other, right? I've already completely exploited what makes the subspace, and so that's that. And if you look at it, you can argue then that a nice basis for W would be formed from just these exactly what we have here. Like, so this can be rewritten as E11 minus E33, E22 minus E33, and then you got the rest of them, E12, E13, E21, E23, E31, E32. All right, so it's clear that they span W from this calculation here, right? Because I took an arbitrary thing in W, and I showed you that it's a linear combination of these objects, these 8 objects. So clearly, it's already clear. Already clear that the span of beta is, W. Now, how about linear independence? Well, linear independence, consider A equals to 0, right? But in other words, if I set A equals to 0, that's the same as doing what? That's the same as setting like A11 times E11 minus E33 plus plus, A32, E32, just to get to the point here, equals to 0, right? So this linear combination equals to 0, but look at it. That forces A equals to 0, so therefore beta is linearly independent. I mean, the very calculation that you've already done you can just look at it and say, well, if I set this linear combination equal to 0, that's an arbitrary linear combination of these things, and clearly it being 0 forces this to be 0, which means that, well, all of A11 through and so forth and so on is going to be 0. I suppose, to be clear, from the 1, 1 spot, you get A11 equal to 0, right? And then the other ones, for some reason I'm having a hard time thinking right now. I don't know what it is. Let's see here. Matthew. He's got his space gun over there. Anyway, so beta is linearly independent. Just to give you a sample coordinate calculation, if I had, for example, we'll be talking more about coordinates as we move to the subject of linear transformations, but let me just put it up here. So if I had the matrix, for example, let's see here, 1, 2, 3, 4, 5, 6, 7, 8, and now I gotta be careful. I can't just put anything here. I need this thing to be what's called traceless. This is actually the trace. In fact, you could look at W as being equal to the set of traceless 3x3 matrices over R. Okay, more on that in the next homework. But, mission. What am I saying? So if I say 1 plus 5, in order to be fair, I have to do what? Minus 6, right? And then the sum of the diagonals is 0. So this is actually a legitimate, let's say, B. This is an element of W, right? And, I guess B is a bad choice. Oh well. My beta looks different than my B. It's okay. So the coordinates of B with respect to the beta basis then are what? Well, you just got to look and see, okay, what are the coefficients of these different things? So like, let's see here. If I look at how many copies of E11 do I have? Well, 1. How many copies of E12? Let's see here. Oh, I guess it kind of matters the order I put these in. Okay, I've got 1 of these. I've got 5 of those. I've got, let's see here, E12. 1, 2 is this 2, so I got two of those. 1, 3, I've got 3 of those. How many 2 1s do I have? I got 4 of those. How many 2 3s do I have? I've got 6 of those. How many 3, let's see, 2, 3, how many 3 1s do I have? I've got 7 of those. How many 3 2s do I have? I got 8 of those, right? And the -6 doesn't even come into play, right? Because that's already wrapped into these two guys. All right, so there you go. That's the coordinate vector of this this matrix with respect to this basis. It's a 1, 2, 3, 4, 5, 6, 7, 8-dimensional coordinate vector because this is an 8-dimensional subspace. Now, I think you see my point when I say visualization isn't probably the way to go here, because I don't know about you, I can't personally visualize 8-dimensional things. So there you have it. Oh, fun story. My brother happened to be at a talk at the Institute for Advanced Study, and some of the greatest string theorists living were there, and the speaker was the guest speaker asked them, can any of you visualize, 5 dimensions? And there was universal, nope, well, can't do it. I mean, these are people who have done nothing their whole adult life but work in dimension, in physical theories of dimensions, 5, 6, 7, 8, 26, I mean, that's their entire adult life's work has been working in higher dimensional spaces. They can't visualize it, all right? We don't use direct visualization to understand these things. We use algebra and calculus. This is what abstract math is partly about, is growing past this need to directly visualize things. But I know it's a growing process. It took me a while to give up on visualization. I haven't entirely given up on it yet. I have other pictures, like here, for example. Here's how I mean, you can still kind of draw pictures of things in higher dimensions, but I digress. All right, let's see here, another basis calculation, and then I'll let's see here, example. What if we had something like W is equal to the null space of A, Cartesian product with the column space of A, where A is equal to, let's say, 1, 1, 1, 2, 0, 0. That's pretty simple. Now, let's find a basis for this thing. All right. That's kind of a weirdo example, but it'll serve to show a purpose here. All right, so what is, first of all, the null space of A is what? It is equal to, let's see here, A is what? This is 2 by 3, right? So this is going to be, let's say, V in R3, I'm working in the real case again, such that AV is equal to 0. All right, so this is a subspace of R3. In contrast, the column space of A, well, that's a span by definition. It's the span of, these columns, 1, 2, 1, 0, 1, 0. Technically, it's that, right? And as you can see, that's a subspace of R2 in principle. Now, in fact, I can immediately see that the column space of A is, in fact, R2, because it's clear to me that this matrix has rank 2. By the way, it's immediately obvious that the column space of A is equal to R2, which means, of course, I can use, as a basis for this, I can use E1 and E2. Matthew, stop that! On the other hand, the null space of A, well, I don't know. Let's see. I have to work that out. So, the null space of A, what's the basis for the null space of A? Let's see here. We're going to put these two things together to get the Cartesian product. So, like, in total, W is going to be a subspace of something like, it's a subspace of something that's like R3, a subspace of R3 crossed with something that's a subspace of R2, And you can prove then that it's got to be then a subspace of the Cartesian product of the total spaces there, which of course I'm not going to think of that as R5. I'm actually going to leave that as pairs of 3 vectors and 2 vectors for the sake of, it'll be easier for us to think of it that way. I'll not set R3 cross R2 equals to R5, as that would actually make the problem harder. Okay, so we're going to leave them like that. Pairs of 3 vectors and 2 vectors. Okay, so let's try to get our understanding of null space. What's the null space of A? What's the basis for the null space of A? Well, let's see here. The matrix 1, 1, 1, 2, 0, 0 reduces to what? So we just do, I don't need to, I mean, I'll just, so 1, 1, 1. Oh goodness, why don't I just do this? So that's really, I don't know, I guess you could go different ways. I'll subtract 2 of those. 0, minus 2, minus 2, right? So that was row 2 minus 2, row 1, obviously. And then, of course, I can do row 2 divided by minus 2, 1, 1, 1, 0, 1, 1, and then finally row 1 minus row 2 just to complete the backwards pass. It was not too eventful. 1, 0, 0, 0, 1, 0. Okay. Actually, I kind of knew that was going to happen because of that already. But anyway, there it is. A little more practice. There's the reverse echelon form of A. All right. All right, so basically then, we have, if we have V equals to, say, x1, x2, x3, and we have AV equals to 0, well, from this I can see that x1 is equal to 0 and x2 is equal to 0. So that's kind of a boring example, but it's instructive too, because x3 is free. That's important. That doesn't, I mean, students have a tendency to set x3 equal to 0 in such a situation as this, which is, oh, so unfortunate, because it's not 0. It's totally free. In other words, you're, you know, you're, what's the word here? What happened? Sorry. No, it's fine. So your null vector here, man, something seems wrong. What have I done? Oh man. See, I guess I got to keep writing. So it looks to me like my null vector should be 0, 0, and then whatever. And yet, if I go back and check that, that doesn't work. So something is wrong. See, I can see just from looking at A. So I've done something wrong in the row reduction there. I'm not sure what. I mean, I can just look at it. 1, 1, 1, 2, 0, 0, and I can see, just eyeballing it, that 0, 1, minus 1 is what I'm looking for. See, because that's 1 minus 1, and then 0, which of course is 0, right? So therefore, you know, 0, 1, minus 1 is in the null space of A. In fact, the null space of A is one-dimensional, which is to be expected, right? Null space plus column space. Rank nullity theorem says we should have this plus this is equal to the number of columns, which is 3. So 1 plus 2 is equal to 3, all right? So what did I do wrong up here? I did something wrong. All right. If he'll stop his space gun long enough for me to calculate. Let's see here. I blame Frozen. Let's see here. So for those of you who already see the error, I'm sorry for this. It must be aggravating to watch this. Oh, duh. Look at that. Idiot. Does this make this be 0? No. Stupid. Okay, so we do get x1 equal to 0, but we do not get this. This is incorrect. What we get is that x2 plus x3 is equal to 0, which is way more interesting because x3 is not free. Well, you could make x3 free, but if x3 is free, then x2 is minus x3, right? So if we look at this, this is 0, x minus x3, x3. In other words, x3 times 0 minus 1, 1. Or I have this with the opposite way around. But anyway, you see there you go. That's either you can either use this or that, I mean, or whatever multiple of that you want as a basis for the null space. Fine. So let's look at it then finally. All right, we got W in W implies that W is equal to what? W is equal to, say, x comma y, such that what? Such that x is an element of the null space of A, and y is an element of the column space of A. Right? And in other words, that would be something like so that means W is equal to something like x comma 0 plus 0 comma y, right? And continuing this silly example, I can prove that, excuse me, let's see here. What I would do is I would use 0, sorry about that. Sorry, let me try this again. 0, 1, minus 1, comma 0. All right, that gets this x term. And then I do 0, comma, and let's see, what's the basis for the column space? Well, whatever you want, really. By the way, this is, to be clear, that's 0, 0. It's silly degenerate 0. So over here, I have 0, 0, 0 to be annoyingly explicit about what's going on here. 1, 0, comma, 0, 0, 0, 0, 1. And this would be a basis. This would be a basis for the Cartesian product of the null space and the column space. Let's see here. So what I have here, of course, is these are basically 0, comma, the basis for the column space, and this is the basis for the null space, comma 0. Let's see here. For example, then, if I have the vector W, just to be explicit about this for a second, if I have the vector W is equal to something like, let's say, 3 times 0, 1, minus 1, comma, let's say, 7, 8, whatever, right? You can rewrite this as 3 times 0, 1, minus 1, comma 0, 0, plus 7 times 0, 0, 0, comma 1, 0, plus 8 times 0, 0, 0, comma 0, 1. All right, at this point I should really come up with some names for these guys. Let's call this thing V1. Let's call this thing V2. Let's call this thing V3, right? In other words, what I have is I've got 3V1 plus 7V2 plus 8V3 is W. Therefore, the coordinate vector of W with respect to the beta basis is 3, 7, 8, where beta is V1, V2, V3. Now, there's a hole. I showed you basically that beta is, spans the thing, right? I guess it remains to be sure that this is linearly independent, but I invite the reader to check that, the watcher, whatever you want to call yourself, you can show that beta is linearly independent without a lot of trouble. So there's another example of a basis, which is, well, I guess is kind of out there. So, all right, finally, just to conclude this little arc of the lecture, let me just say I added a couple things to chapter, chapter 3. In particular, I just would draw your attention to the fact that I have added a proof of this theorem 3.77, that the dimension of u plus w is the dimension of u plus the dimension of w minus the dimension like that. So I guess a good example for that would be something like, you know, so here's the like the zx plane, right? And then so that might be like your u. So the span of E1, E3, and then the W you could visualize as something like this guy. I don't know, maybe the XY plane, right? So in my notation, W span of E1, E2, right? Now U plus W is a set of all linear, set of linear combinations of vectors. So maybe here's the origin. I don't know. So U plus W is in fact all of R3, because if you take linear combinations of vectors in this space and vectors in that space, well, you can get everywhere, right? So on the other hand, the intersection of U and W geometrically, right, it's just this guy. That's U intersect W, which is what, the x-axis in this case. And this is an example, right? So like the dimension of this is 3, and as you can see, 3 is equal to 2 plus 2 minus this dimension of that, which is 1. So here's an example of this theorem. But anyway, the proof is a lot of fun, and basically what I do is I take a basis for the intersection, all right? And I extend it two different ways. On the one hand, I extend it to complete a basis for the subspace U. On the other hand, I extend that basis to complete a subspace, the subspace W. So I add W1 through WE, or I add U1 through UD. I say W1 through WE. These guys are not in the W, these guys are not in the U, but the V's are both in U and W because they're in the intersection. And then what we do is we argue that the basis for the sum is formed by taking the ones in the intersection, the ones that are only in U but not in the intersection, and the ones that are only in W but not in the intersection, which of course is the intuitive thing, right? And once you have that, well, then counting gives you the result, all right? Because you can add the number of things and it works out, right? But the trouble then really is to show, in fact, that this is a linearly independent set. And that takes a little thinking. And the thinking goes something like this. You just, you basically just set a, where was I? Well, first of all, you argue that it spans. That's easy. That's not hard. You'll understand that when you think about it. Linear independence, though, you set a linear combination of them equal to 0, and then what you do is you solve for the ones in the intersection, right, like that. When you do that, or rather, goodness gracious, where did it go? So if I solve for rather these ones, the ones in the intersection minus the ones in the goodness gracious, the ones that are in U but not in the intersection, I get these ones over here. Well, those are in W. But on the other hand, oh man, I lost track of what I was going to say. Well, anyway, you end up being able to argue that minus y is both in W on the one hand, but also in U on the other, all right? And so what that means is that it's in W and in U, which means that it's in the intersection, which then means that you can equate coefficients of this with a linear combination of things in the basis for the intersection, which then forces the things which are not in the basis, these guys, to be 0. Then once you have the beta j's are 0, you can go back and make the same argument and force the coefficients of the gamma k's equal to 0. Once you have both of those are 0, then you can go back over here and force the alphas to be 0. So it's a little sneaky, but you get it after a little bit. And I just want to tell you, I wrote up a fairly careful argument. I think it's a slight improvement what's on your in terms over what's in your textbook. And I'm going to give up trying to tell you more things at the moment. Thanks, guys. Sorry.